Okay. So we missed the first 5 minutes. So let's go ahead and distribute this and find lambdas. So foiling this polynomial, we get a 7. We get a lambda square. We get negative lambda of negative 7 lambda plus 9 equals 0. Combine like terms, so we get lambda square minus 8 lambda plus 16 equals 0, right? Well, what happened? I know what I did. I'll fix it, don't worry. I zoomed in really, like too much. Okay. Okay, so we factor this to lambda minus 4 squared equals 0. And as you can see, lambda 1 equals lambda 2 equals 4, right? Now let's go ahead and find the eigenvectors. So find the eigenvectors. We subtract lambda from the main diagonal, so we get 1 minus 4, negative 3, 3, 7 minus 4, and we multiply it by some vector x and y, a, b, it doesn't matter. And as you can see, this becomes negative 3, negative 3, 3, 3, multiply x and y equals 0, 0. Okay? And both given the same equation, negative 3x, negative 3y equals 0. 3x plus 3y equals 0, and both giving you basically x plus y equals 0. And you can, solve for one of them, x equals minus y. So one of the eigenvectors, and as you can see, this is only giving you one eigenvectors. So, and that one is nothing but, let's just go with 1 minus 1, or, negative 1, 1, or as long as it satisfies that equation. The one that I'm going to pick is negative 3 and negative 3. You'll see why later. That means this is only going to satisfy and gives one of these solutions. So x1 of t, we know how to form that one. That's v1 e to d lambda 1, in this case lambda, or let's call it lambda 1, we call it 4. So in this case, we only have negative 3, 3 e to the 4t. Right? So, and there is no way, that's the only eigenvalue. We could only find one eigenvector. What's the other eigenvector? That's one question. So here, the question is, what's the, or how we find other vectors? So what's the other eigenvector? Because we want to set up the other solution, right? Okay. Let's talk about, and by the way, that's the form of, one page of my notes. So it's going to be 2 columns, and then I write down another column, and then I go next page, do the same. So let me zoom into the right column with 140%. I already set up the right zoom number. Do you guys have any questions? Anybody has questions so far? Let me know in the chat. Okay, so let's do some definitions. And by the way, for the example that we just did, that eigenvalue, lambda equal 4, is not complete, right? Because it doesn't have 2. It repeats twice, but it doesn't have 2 eigenvectors. It only has 1. In fact, that difference 1 is the defect of this eigenvalue. Like, it's not complete, of course, because it doesn't have the same number of, as being repeated. Since it doesn't happen, call it a defective eigenvalue, and it has a defect of 1. Let's write down that definition. So if, lambda, and let's suppose is repeated. Correct, Kyle. I'll eventually, at the end of the session, I'll make a PDF out of this. Let me show you. So I finish this note, I hit export and then I do PDF, as you can see, and I do share. I'll email it to myself and then I post it on e-learning. So I've done this already this morning. It works nicely. So you don't have to take notes. Just listen. And also, I'm recording the session and I'll put the MP4 file on there. I'll post it on e-learning. Okay, going back to this definition. If lambda repeated k times, or multiplicity, k, has only, so it doesn't have the same number of eigenvectors. So it's a number less than k. For example, if it repeats 7 times, you can only find 3 linearly independent eigenvectors. That means 4 other eigenvectors are missing. So let's suppose it repeats k times, but it only has, p, which is less than k, linearly independent eigenvectors. First of all, or then, lambda is called a defective eigenvalue. And that gap that we just talked about, the difference between the two, so in this case, I want to call it D, which is K minus B, is called the defect of lambda. For example, for the one that we just did above, let me go to the other half of our page. So the one in the bottom that we just did. So here the multiplicity of 4, so lambda equal 4 has multiplicity 2, but it only has one linearly independent eigenvector. That means it's defective, and defect is 1. Okay. Okay. Now, question is, what do we do for this case? Right? All right. So I mentioned that. And, for the example above, for example above, K was 2, right? Let's start with this. So we know for the matrix, we had lambda was equal, lambda 1, lambda 2, both were equal 4. We were able to find only one vector v1, which was, I think I picked -3 and 3. So I can set up x of t as, -3, 3, and then e to the 4t. Now, let's naively or intuitively, similar to what we did in chapter 5, I think someone mentioned it in class, we would say, in fact, the question is, what should x2 of t be? Because we don't have a v2. So what do you guys think is going to be? You can go ahead and open your mic and let me know what you think x2 of t should be. Oh, what am I doing? I only put a question mark. Well, if you think like chapter 5, when it was a repeated root, what did we do? We multiplied it by t, right? So someone might say, well, go ahead and put a t right there, like put a t here, and that would be the second solution. Okay, let's try that, okay? And see, maybe it works. But if it doesn't, we try something else. So let's start with this. Let's naively suppose the other solution is, the V1 that we already found, simply multiplied by t e to the lambda t and assume that's the solution. So let's naively assume this is the other solution to the system of equation that we started with, this guy. Okay. And by the way, we know V1 is not 0. Okay. So if that's a solution, then it has to satisfy it. It has to satisfy this system. Meaning x2 prime should be a x2, right? Let's set up this equation and see what happens. So I'm going to take the derivatives are happening with respect to t, right? So with this x2, derivative of that with respect to t, as you can see, you do a product rule, so it's going to be v1 e to the lambda t plus derivative of e to the lambda t, so lambda goes down, so lambda v1 t e to the lambda t. And on that side, you only have a times x2, right? So it's going to be a v1 t e to the lambda t, right? Okay, so let's sort of, treat this as an equation and solve, see what we get. We can divide everything by lambda t because they all have lambda t, e to the lambda t, sorry. So let's do that, and we get v1 plus lambda v1 t equals a v1 t. And we can treat it as a polynomial, right? This side we have a vector polynomial, degree 1, t to the first, we have sort of the same thing. And we have a constant term on this side, v1, and we have no constant term on that side. And that tells us, these two have to be the same. These two have to be the same because they have t to the first power. So the coefficients have to be the same. That means EV1, AV1, sorry, equals lambda V1. And the other one tells us V1 has to be 0. But that can't be true. In fact, this gives us a contradiction. Now, someone tells me where the contradiction is. In fact, between these two equations, I want to number them. 1, 2. One of them is absolutely right, like we already know it's correct. The other one can't be right. Which one is correct and which one is not correct? Tell me in chat room. So type the number that is correct, that we already know is correct. Alex says 1. Olivia says 1. People saying 1. Me. Okay. I'm gonna someone turn their mic on and tell me why the second one is not correct.
At the top of the page, you put V1 can't equal 0.
That's absolutely right. In fact, that's a contradiction with this assumption. I mean, that's not even an assumption, that's a fact. The eigenvector cannot be 0. Thank you. So this is a contradiction with the fact that, eigenvector cannot be 0. And where is this contradiction coming from? From the assumption that we made. Where did we make that assumption? Right here. So let's naively suppose that this is true. That means this form cannot be the second solution. We have to come up with something different. Okay, we can't just multiply by t. All right. So let's go with another form. Well, what form did we choose? The form we chose, we said let x2 of t be, v1t, and then multiply by e to the lambda t. Let's throw something else in there. let's see if we can find a vector v2 that might make this one the second solution. And we do the same process. We assume it's a solution, right? I mean, think about it. The next simple thing that you can add it to this solution, like we already had the v1t part, we had the e to the lambda t part. So what's the next simple thing that we can add to it? Someone can say, you know, raise t to the second power, or just throw another vector in there, right? So let's try this one and see if it works. So let x2 of t be this guy, and assume is the solution. Okay. And again, if you get a contradiction, that means this one's not working. But let's see. So since it's a solution, then you know it has to again satisfy it. The prime of that has to be ax squared. So let's derive that. Of course, it's a product, but we have a v2 term in there. So derivative of the first part again is v1 e to the lambda t, right? Plus the other one, a lambda goes down, so we have v1 t plus v2 lambda e to the lambda t. And the right side has to be simply a times that. So it's a times v1t plus v2 e to the lambda t. Okay. Let's simplify. And once again, go ahead and divide everything by e to the lambda t, because you have e to the lambda t and it's not 0. So let's drop e to the lambda t. So I'm gonna distribute and combine like terms if I can. So I have a v1 plus lambda v2. There's no t in those two terms. I'm talking about this one and that one. Plus v1t. Oh, I'm missing a lambda. Right? All of them are missing the. Actually, I did multiply by lambda. So lambda v2 for that one. Plus lambda v1t equals, now here I have a v1t plus a v2. And again, I have terms that have t in them, and I have constant terms with no t variable. So let's set them equal to each other. So I get these two equations. A v1 equals lambda v1. I forgot to ask you a question. You said equation 1 is correct. I forgot to ask you why it is correct. Well, I'll ask you this time. And the other two is a v2 equals lambda v2 plus v1. And I can write the second one in this. I want to bring this term to the other side. Factor v2, v2 is a vector, right? So it becomes a minus lambda I equals v1. And the second one is the same, right? Or, I can even write a minus lambda I. In fact, this helps you to answer the question. Why? So this one, number one again, is correct. And we already know it's correct. Now, someone open their mic and tell me why the first one is correct. Oh, Alex is asking where did I come from? So by I, he means this matrix. This is, again, this is the identity matrix. It's the n by n, 1, and the main diagonal on 0. So since I'm factoring vector v2, if I simply write a minus lambda, it doesn't make sense, because remember, lambda is a scalar and a is a matrix. And matrix minus a scalar doesn't make sense, right? So when v2 comes out, in fact, this lambda is simply lambda minus I, same as a minus lambda I, and then this determinant set n equals to 0. It's the same. So that's where that I is coming from, unless the multiplication wouldn't make sense. Like a minus lambda alone times v2 doesn't make sense. It has to be a matrix multiplication. Now, Did I answer your question, Alex? Okay. Anybody else has question before someone answers this question? Why that equation is correct? Why we already know a minus lambda I times v1 is 0. I'm waiting.
Wasn't it a given equation earlier?
Well, let's go up again, okay? What did we already assume? In fact, we're doing this for example, but it can be true. So we started the system A equal x prime equal ax, right? And we already know we have an eigenvalue that is repeated twice. And we only found one of the eigenvectors. And how did we find this eigenvector? Didn't we find it by setting or solving, not this one, but solving that equation? And we solved it, for x and y, and we got v1, right? This is what we solved. If I go to the bottom of the left column, it's right here. So we already found v1, and we know v1 satisfies this equation. And this equation, I mean this guy. So we know v1 is a solution to this equation, the whole a minus lambda I times v1 equals 0. So of course this is true, because we already found it, right, using this, solving this equation. So for that reason, like that one, like doesn't tell us anything significant. We already know this. Now we go to the next one. Now this one has no contradiction. Well, I have already found a vector that I know it's not 0. And remember, we just simply assume, let's see if we can find the vector v2. I'm going to circle it right there. Let's see if there's a vector v2 that if I add to this, it becomes the second solution. Well, nothing happened. There's no issue with this. There's no contradiction. So as long as I can find a vector v2 satisfying this equation, then I'm good, right? Then this can be, the x2 can be solution. So I'm going to write it down. Thus, as long as we can find a vector v2 for which a minus lambda I times v2 equals to the vector that we already found, and we know what it is. So this is known. This is known. Okay? That was a terrible one. So that was the vector we already found. So this is known. And we simply solve that system. That's it. And we find, and again, there's going to be infinitely many solutions with v2. We only get a non-zero. So let me emphasize here, v2 is non-zero. So as long as we can find a vector non-zero vector v2 that satisfies this equation, then there you have it. X2 is v1 plus this new v2 together, and then e to the lambda t. Good. All right, let me zoom out so you can see this whole thing. Fit height. So it's going to look like that, okay? Let me put new page. You guys have any questions? Does it look very dense? Or looks good? I'm going to add a second. I have a very modern ruler here. You're gonna laugh if you see it. So let's go to the left. Jacob is saying this is going much smoother than the physics lecture. Well, glad to hear that. Oops. Second. Okay, so let's, summarize what we said. So I'm going to call it, algorithm for the case when k was 2, that was multiplicity, and defective was 1. And we can repeat this, for multiplicity of 3 and defective 2, okay? In fact, right after this, I'll add that. So let me write down our assumption. So suppose we have a system x equals ax, and we have two eigenvalues, okay? Lambda 1 equal lambda 2, equal to the common value of lambda. And v1 is already found, right? That's the only eigenvector that you can find because of that guy. Then let's do this way. Then this is what you do. First, find a non-zero vector, vector v2 such that a minus lambda I, these are all known. V1 on that side is known. All we have to do, we find this vector. So it's like we set up this system and we find V2. And I'll do an example, you see how it goes. And step 2, then we form these two solutions corresponding to lambda, right? Because we have two of them. And these are the solutions. X1, as I said, was just a normal V1 e to the lambda t. And X2 t is V1t plus V2 e to the lambda t. So that the general solution is C1 x1t plus C2 x2t. Okay? All right, now let's do, in fact, let's continue the example we were just talking about, right? So the example was, I think we found the eigenvalues of this guy, 1, -3. It's the 2 by 2 that we just found, right? X. So we already know the eigenvalue is 4. And we found one of the vectors. Well, let's go to the previous page, okay? And I'm going to point out to it. It's right here, right? We found 1 and -1. And, as long as those two components satisfy this equation right there, it doesn't matter. So it could be anything. Now, the one I picked, I already solved this, so I know what's going to make it easier. But it doesn't matter. As long as you pick a non-zero vector, it's going to make it work. So the one I'm going to pick is -3 and 3. And you're going to see why. So I'm going to pick vector -3 and, okay. All right. Now we find a V2 non-zero such that, all right, what was the equation? A minus lambda I times the V2 that we're about to find. So let's go ahead and call it again X1 equals the candidate you already found or picked for V1. A minus lambda I, basically, it's the same matrix. You just take away the value of 4, eigenvalue from the main diagonal. So that's going to be 1 minus 4, negative 3, 3, 7 minus 4 times xy equals. And it's very easy to remember. Normally, to find eigenvectors, what would you set the right side equal to? 0, 0. In this case, you set it equal to the eigenvector that you already found. What is the one that I picked? Negative 3 and 3. If someone picked 1, negative 1, negative 1, 1, if someone picked, I don't know, 10 minus 10, it doesn't matter. It's just a multiplication by a scalar at the end. In fact, we can check that. Okay, now let's go ahead and solve this. So whatever I solve, whatever I find here satisfying this system, I'm going to call it V2. Okay. Let's simplify that matrix, and we already know what it's going to look like. Negative 3, negative 3, 3 and 3 times x and y equals negative 3 and 3, not 0, 0. And as you can see, they're both giving you the same equation, just by a negative, multiplication. I guess you can see why I picked negative 3 and 3, because, it nicely goes with the coefficients. Whereas if I picked, 1 and negative 1, it wouldn't be as easy as this one to deal with. Shift things up. So they're both going to give you x plus y equal 1. And that's the straight line. In fact, this is the equation of this line, right? That's this straight line right here for x and y. Now, any point on this line is going to make it work. It doesn't matter what you pick. So you can pick, 1, 0. You can pick 0, 1. You can pick half and half. Doesn't matter. It does not matter. In fact, 0, 0 doesn't even satisfy this, so you don't even have to worry about it. Let's see. Alex saying, if you solve for x for v1, do you have to solve for x for v2? Nope. No. Let's go back up. So, so I'm assuming you're saying when we found x1, let me go back to the page 1. So you're saying down here we solved for x and we picked our candidate for v1. Do we have to do the same thing on this guy and solve for x? No, it doesn't matter. As long as you can find any vector satisfying this equation, satisfying this equation, it's a check. It doesn't matter. Okay? Well, so let's go ahead and, pick this as V2. So for that reason, we already know what x1 was, right? So our x1 was v1 e to d lambda t. Let's rewrite it, it's okay. So negative 3 e to the 4t. And x2 is, parenthesis open, v1t plus v2 e to the lambda t. Let's write down those vectors. So it was negative 3 and 3 times t plus vector, we picked 1, 0. Close it, and then e to the 4t. Right? And, you can simplify this to put them together basically. It's going to be this single vector, negative 3t plus 1, and then 3t times e to the 4t. And eventually, again, the general solution is C1, the capital X1t we found up there, and then C2, X2 of t. Okay? Any questions so far? So that was that. All right. Now I'm going to go ahead and generalize this for, you know, any eigenvalue of any multiplicity and any defect.
Sorry to interrupt, but how did you get the V2 1 over 0?
You
Because
mean
you
1
had
and
the
0?
x plus, yeah, because you had the x plus y equals 1, and I was wondering how you got 1 over 0 and those three.
Okay, just come up with a pair of number that satisfy that equation. Any pair of number x and y where they sum up to 1.
Ah, okay. Perfect. Thank you.
As you can see, the components of these vectors that I have here, right there, they all add up to 1. So you can pick 7 and negative 6, 10, minus 9. As long as they add up to 1, it's a good vector.
Okay, perfect. Thank you.
Yeah, guys, feel free to, open your mic and ask questions. Okay. So that was that. Now let's go ahead and write down the generalization. I have another proof for the case of, defect 2, but if you're interested, I can explain it during office hours. So let me just go and write down the generalized case. So, in fact, this is called for defective eigenvalues. And the eigenvectors we find is called generalized eigenvectors. Okay? That's what it's called. So, let's talk about another situation and then I'll write down the whole generalization. So, let's suppose lambda has multiplicity k equal 3. That means it's repeated 3 times. Okay? And is the defect is 2. That means we only found one eigenvector, right? So D equals 2. Like 2 eigenvectors are missing. So 2 eigenvectors are missing. Okay? And so let's assume the one found is V1. So only found one eigenvector. I'm going to call it here V1. Okay? We already know how to find the second one, right? So the first one solution is V1 e to the lambda t x2t was V1 t plus V2 e to the lambda t, where you find V2 this way, a minus lambda I times V2 equals V1, solving that system. All right, the third one, first of all, the third one basically it's, the same sequence. In fact, how did we find V1? For the V1, we solved this system, a minus lambda I times V1 was 0 vector, right? Initially, we set the right side equal to 0. We find V1. Now, pick that V1, put it on the right side, solve the same system, and you find V2. Now, put V2 on the right side of a new system. And the vector that you find here is V3. If there were 4 of them, you basically continue this process and you find the sequence of all those vectors. Okay? But the solutions are going to be different. So the third one, x3, is going to be, of course, it has e to the lambda t in it, right? All right, so we're going to sort of extend this and put it here. I mean, you can sort of see. Started at V1, and we increased the power by 1, and we got to the next one. Of course, a term was added to it, which is V2, right? So the next one is going to be the second power of t. So it's going to be, I should have left more room, so let me raise this. So it's going to be, V1 t squared plus V2 t plus the new vector V3 that we find. E to the lambda t. There's one simple thing that I want to point out, and that's the coefficient of half that you're going to have to add to V1. And that's a very simple, check. In fact, you can start with no coefficient, like simply assume it's 1. It has to satisfy the system, take derivative, set up those coefficients just like the one we did, and you'll see, a half would adjust the coefficient of 2 that is going to show up on that system. So a half is going to take care of it. Right? Now, for example, let me add one more thing. Let's say the defect is 3, right? That means we're going to need x4 of t. First of all, you find v4 here in a similar way. So when you find v3, put it on the right side of this equation and then solve this system. There you go. That's your v4. And the corresponding solution for that is, I'm going to write it down, and then you tell me what coefficients do I use. So it's going to be v1 third power of t plus v2t plus v2t squared, v3t plus v4. Now, I'm going to need some coefficients here and here. You should sort of be able to see the pattern. Now, someone tells me, so Alex says 1/3 and 1/2. Your 1/2 is correct, so I'm going to go ahead and put 1/2 in there. That's 1/6, and I got it. Well, and I got it. I know how it is. Simply anti-derive each thing. Think about it. Let me start with this. If you have A1, you take antiderivative with respect to t, you get A1t plus some constant. Go ahead and call it A2. Same thing, antiderive that one. So you get A1 t squared over 2 plus A2t. You need a constant, call it A3. Antiderive that one. T cubed over 3. So it's a 1/3 times 1/2 is going to be 1/6. A1 t cubed plus t antiderivative is t squared over 2. So that's, half A2 t squared plus A3t. You need a constant. Let's go ahead and call it A sub 4. And then you can continue like that. And, for each solution, you need a new vector. So you already find V1. Use that on the right side of that system to find V2, right? A minus lambda I, V2. And keep going that, until whatever vector you need. So eventually you need, for example, in this case, V4. We find it the same. It's a very simple process. And you don't have to, memorize it. If you follow this pattern, you know where it gets to. Let me erase some of these guys. Because so I'm going to call this, the pattern. Okay. Questions? Let's do, actually, I only have one example left. Wow. So let's do this example. It's an example 3 by 3. Let me write it down. So example, solve the given linear system. In fact, we have 38 people, actually 37 people in the chat. This is the most generalized, I don't know if you want to call it the most, difficult or complicated situation of a linear system in this entire chapter. Because as you'll see, there's going to be a repeated eigenvalue 3 times. It's a 3 by 3 matrix. Let me write down a system. So x prime, which is, x prime, little y prime, little z prime equals to this 3 by 3 matrix. 0, 1, 2, negative 5, negative 3, negative 7, 1, 0, 0. That's a 3 by 3 matrix, and it's multiplied by x, y, z. And of course, the matrix form is AX. So simply, I'm calling this matrix A. So that's the most intense question and example that you might get. That's it. I'm not going to give you a 4 by 4. That's the case when you get a one single eigenvalue repeated 3 times, and you're going to have to find, the 3 linearly independent eigenvectors. So let's go ahead and do this one. If you can master this one, you're good to go with chapter 7. Okay. So question before we continue this. And by the way, do you guys want to take a break? It's 4:50. So hit yes, type yes if you want to do a 5-minute break.
So for an x sub 5 of t, would it be 1/8 v1 to the t to the 4th?
You're talking about if I continued this pattern to the next term?
Yeah. So if it was t to the 4th.
No, it would be 24.
24. And so that's
Think
why.
about it. Yeah, what is the antiderivative of t to the 4th? 2 to the cube, sorry. T to the 3rd. What is antiderivative of that?
5 to the 1/5. Or t 5
to the 4th. T to the 4th over 4, right?
Oh, yeah.
Antiderivative of t to the 3rd is t to the power 4 over 4. So if you multiply this by 1/6, what do we get? We get 1 over 24, right?
Okay. All right.
So it would be, the next one would be 1 over 24. The next coefficient of that would be 1 over 6, 1/2, In fact, coefficients are going to be 1 over 4 factorial, 1 over 5 factorial, 1 over 6 factorial, and so on.
So you just multiply that by the coefficient it currently has.
Yes, exactly.
Right.
All right, let's do a 5-minute break. It's 4:53. In fact, let's do it, 7 minutes. So we come back at 5. We'll do this example, and we're good to go. I want to go ahead and mute my mic, okay? All right, guys, I'm back. So let's go ahead and solve this system. And then I can have you guys ask questions if you have any. If you've been studying, if you have a question on other sections, you can go ahead and ask them. Okay. So, well, first thing we need to find eigenvalues, right? So, finding eigenvalues. For the matrix, we subtract lambda from the main diagonal. 1, 2, -5, negative lambda. 1, 0, and then minus lambda. We go ahead and do it about the last row because there's a 0 in it. Makes things easier. So we're going to get 1 times 1, 2, -3 minus lambda and minus 7. Throw a little bit of distance between. And then negative lambda times the other 2 by 2. So minus lambda 1, -5, -3 minus lambda. Okay. Let's do the determinant of 2 by 2. So it's -7, this one. And then minus 2 times -3 minus lambda. Let me check my work again. I don't want to miss a negative and then confusingly look for it. Then negative lambda times, put in bracket here. So that one is negative lambda times -3 minus lambda plus 5. Okay. And of course equals 0. All right, so we have a -7 plus 6 plus 2 lambda minus lambda. Let's simplify right there. So we get 3 lambda plus lambda square and plus 5, right? Let's distribute this lambda and we can combine these two. So we get a -1 plus 2 lambda. Careful that there's a multiplication here. So don't subtract these two because order of op says you have to do multiplication. So minus 3 lambda square negative lambda cube and minus 5 lambda equals 0. Okay. We have two terms that we can combine. So we have negative lambda cube, -3 lambda squared, minus 3 lambda minus 1 equals 0. Everything is negative, so let's multiply everything by negative, right? So we get lambda cube plus 3 lambda squared plus 3 lambda plus 1 equals 0. Now, this factors. What does it factor to, guys? Open your mic and tell me what it factors to. Beautiful. We all got it. So it's lambda plus 1 cube equals 0. That means lambda plus 1 is repeated 3 times, meaning all 3 eigenvalues are the same and they're the common value of -1. There you go. Okay. All right. Now let's see. So we already know, we only know, 1 or lambda equal 1 has multiplicity 3. We don't know what the defect is, right? Oh, you're saying scroll up a bit. I can because it's the bottom of the page, to be honest. So I don't know if it helps right now. Okay, let's go to the next page. So let me zoom out of this completely. Okay. So I go ahead and fit it with height. Let's go to the next page. Okay. So lambda repeated 3 times. Oh, by the way, let's divide it to 2 columns. One day I'll reveal what I'm, drawing this line with. You guys can use your imagines. So 40. Okay. All right. So lambda 1 equals lambda 2 equals lambda 3. They were all equal to -1. So what is our wish? The wish is we want that this guy gives us, 3 linearly independent eigenvectors. If that happens, it's, the best case. Let's see if it happens. So we subtract this from the main diagonal, write the matrix, and then subtract. So it was 0, -1, 1, 2, -5, then it's -3 minus, oh, by the way, it's minus -1. Sorry, right? It's minus lambda. It's A minus lambda times V equals 0. So when you subtract minus from the main diagonal, it becomes +1. So it's -3 plus 1, -7, and then this one is 1, 0, and this one was 0, so it's -1, which is +1 itself. Okay. So let's see what vector we get by solving this one. And remember, to solve the first one, you're setting the right side equals 0, right? So hopefully it gives us, 3 linearly independent vectors. Or at least 2. Like 2 is better than 1. 1 is the worst case. Okay, so let's go to multiply. So we get x plus y plus 2z equals 0, right? And what is the other one? For the other one, we get -5x minus 2y minus 7z equals 0. And for the last one, we get x plus z equals 0, right? And let's go ahead and solve everything in terms of x, or maybe z. Let's solve for z. So x is -z from the last one. And if you plug it here, we get -z plus y equals, oh, plus 2z, sorry. Plus 2z equals 0. And this one tells us, okay, I'm plugging -z for x, so it becomes 5z minus 2y minus 7z equals 0. They should give us the same thing. Let's see. So what is this one telling us? This one says y plus c equals 0. And what is this one telling us? That one says -2y minus 2z equals 0, which is the same thing, right? If you divide by 2, so eventually, let me write it down. So it says -2y minus 2z equals 0, which is, again, y plus z equals 0. So y is minus c, right? Meaning the vector we set up for our eigenvectors x, y, z is, so x was -z, y is -z, and z itself. That means we are depending 2 of them, right, onto 1 of them. And if you pull out z, as you can see, you get -1, -1, and 1, right? Or if you want to just have one negative, you can do -z and then 1, 1, -1. It doesn't matter. It has to be a non-zero multiple of that vector. It doesn't matter what you pick. And I don't know what the, next system is going to be. So I'm going to stick with this guy. And by the way, how many eigenvectors are we getting? Only one. We found only one eigenvector. How many are we missing? Let's see who. How many eigenvectors are we missing? Two. Correct. We need two more eigenvectors. How do we know we need two more eigenvectors? Because the initial eigenvalue, this guy, was of multiplicity 3. It repeated 3 times. So we do need 3 eigenvectors. We only found one of them. So we need 2 more. Okay. So what was the algorithm? So we find V2, the next one this way. We set up the same matrix that you used to solve this equation, the one in which you took out, the eigenvalue from the main diagonal. So the same matrix, I'm going to write it here. It's 1, 1, 2, negative 5, minus 2, negative 7, okay? 1, 0, 1. You multiply by x, y, z. And you set it equal to what? Someone open your mic and tell me what we set it equal
to. V1.
V1. Good. Does it matter what candidate of V1 we pick? No.
No.
As long as it's not 0, as long as it's not a non-zero vector, it doesn't matter. I mean, the only thing is you might get equations that you come up with rational coefficients, just like the one that we did, that was purposely I picked -3 and 3, so eventually we don't get any, fractions. But that's very hard to avoid unless you do the whole problem. So let's go ahead. At least we know this one has 2 negatives, right? And that one has 1 negative. So let's go with the one that has 1 negative. So let's set it equal to that one. And once again, it doesn't matter, because eventually you're going to adjust these numbers with the C1, C2, C3. Okay? All right. Well, same thing. In fact, you're going to get the same equations that you get here. I'm going to highlight it up there. So you get the same equations, except the right side, instead of 0, 0, 0, you have 1, 1, minus 1. Simple as that. Okay? So let's write them. So you get x plus y plus 2z equals 1, negative 5x plus or minus 2y, negative 7z equals 1. And the last one is x minus z equals 1 again. All right. So similarly, let's go ahead and solve out of, for example, x, that one. So let x be 1 plus z, okay? Set it in the other two equations. So we have 1 plus z plus y plus 2z equals 1. And the other one is I have to multiply this guy by negative 5, right? So it's negative 5 times 1 plus z minus 2y minus 7z equals 1. Let's continue. Let's see if I can fit it right there. 1 and 1 cancel out, so you get y equals negative 3z. Agree on that? And I assume you're going to get the same thing with this one. Let's see. Maybe not. So in this one, we get, let me check what it was. Yep, that's equal 1. So x is 1 plus c. We set it up there. And have it. So in this one, we get a negative 5, negative 5z, negative 2y minus 7z equals 1. What do we get for this guy? So we have negative 5. Let's bring it to the other side. We get 6. Hold on. Someone is asking this question. Should the last equation be equal to minus 1? Which one? Oh, you're right. You're right. You're absolutely right. So this is x minus, it should be x plus z equal minus 1. Okay. So x plus z equals negative 1. Okay. So that changes things. Then we have x equals minus 1 minus z. So x equals minus 1 minus z. What else it changes? So here we're going to have negative 1 minus z. Am I good now? X plus c equals negative 1. Okay. Solve for x. Plug it here, and then same thing down here. So negative 5 times negative 1 negative z. Okay. Let's erase this and do it again. Let's do it underneath. So this guy becomes, so bring it that side, becomes 2. And then we have y plus z equals 2. We're good? Now I'm guessing this one is going to be the same. We'll see. Mm. 5. I hate negatives. 5z negative 2y minus 7z equals 1. Okay. Bring 5 the other side. Right? Yeah, so we get negative 2y minus 2z equals negative 4. And if you divide everything by negative 2, you get y plus z equals 2. Which is the same, right? So these two are the same. Now let's go ahead and solve for, let's say, y. So y is, 2 minus z. Okay? Well, what did we get? So in that equation, in the vector that we want to find, z is independent. So we have z, we have 2 minus z, and we have, negative 1 minus z. Now let's pick any value for z and get a candidate out of this. So if you pick 0, what vector do we gonna get? We're gonna get negative 2. Negative 1, 2, and 0. But I think I want to do this. Let's pick z. If I pick 1, what happens? I get negative 2. Let's pick 0. It doesn't matter. So if I pick, I get negative 1, 2, 0. Do we have question on this part? On this whole thing and finding this second vector. So this is our V2. So we did this algebra to find V2. If you have question, open your mic and ask. Good to go? All right, let's find the third vector. So same system. Draw a line. So the system was 1, 1, 2, negative 5, negative 2, negative 7, 1, 0, 1. X, Y, Z. All right. We set this one equal to, I circled it, -1, 2, 0. Okay. All right. Same process. So X plus Y plus 2Z equals -1. -5X minus 2Y minus 7Z equals 2. I think next time I want to multiply both sides by negative to get rid of those stupid negatives. X plus Z equals 0. Well, at least the last one came out nicely, right? X equals -Z. Or Z equals -X, it doesn't matter. X equals -Z. Okay. Set it up in the other two. So we have -Z plus Y plus 2Z equals -1. -5 times -Z, it's 5Z. -2Y minus 7Z equals 2. And that's it. We already took advantage and worked with this, right? We don't write the third one down. And these two give us Y plus Z equals -1. And I'm assuming this one's going to give us probably -2, -2Y, -2Z. Yep, -2Y, -2Z equals 2. And it's exactly the same. Divide by -2, and that's Y plus Z equals -1. So basically, the two equations you have are these two. And out of this one, let's go ahead and solve for Y. So we get -Y minus Z. All right, let me mention something here. Just like, finding eigenvectors for all the other examples we have done so far. At any point when you solve a system like this, you should get infinitely many solutions. If you get a unique solution, for example, if you get, I don't know, 0, 0, 0, or if you get just one unique solution, that means you did something wrong in the process, probably something wrong in solving this system. Like check your algebra. Every single system that we have solved, the number of solution is infinitely many. For example, right here, this depends on Z. Depending on what value of Z you pick, you have infinitely candidates. Okay, same thing for this one. So the X, Y, Z is going to be minus Z. Y is -1 minus Z, and then Z itself. Well, this one is very simple. So what value of Z you pick give you a very nice V3. And response, that's the best one, 0. So we get 0, -1, 0. Good. Okay, now let's set up the solution. Okay. So by the way, let's wrap up. So lambda 1 equals lambda 2 equals lambda 3 for this system. They're all equal to -1. We found V1 to be, what was the V1 we picked? The V1 we picked is, so we picked this as a, so 1, 1, -1, 1, 1, -1. We chose V2, -2, 2, 0. V3 is 0, -1, 0. Wall is asking, Z is independent, so you just leave it as itself. Yeah. Remember, out of those infinitely many vectors, you only need one of them, right? So although up there we had Z times that vector, just pick one of them. Doesn't matter. But of course, depending to V1, like depending on what V1 you choose, that V2 is going to be a different. So if I had picked a different V1, this V2 would have been different, and this V3 would have been different as well. Okay. All right, now let's set up the 3 solutions. Oh, My line disappeared. It's okay. Oh. Draw it again. There you go. All right. Now, x1t, that one was very simple. It was v1 e to d lambda 1, or in case, you know, the negative 1t, so lambda t, because all lambdas are equal. x2t, and let's write it down. So that was, I forgot what v1 was. 1, 1, negative 1. It's 1, 1, negative 1, e to d negative t. And then this guy is v1t plus v2 e to the lambda t. So it's 1, 1 minus 1 t plus. You guys remember what 2 is? Negative 1, 2, 0, and let me just so 3 is 0 minus 1, 0. So that one is easy. Negative 1, 2, 0. Negative 1, 0, 2, 0. E to the negative t and x3t. So it was v, there was a half. So there was a half v1t square plus v2t plus v3 e to the lambda t, which was 1, 1, negative 1 t square over 2 plus negative 1, 2, 0 t plus 0 minus 1, 0 close, and then e to the negative t. There you go. You have it. You can, if you want, simplify things so you get 1, 1, negative 1 e to the negative t. x2 of t is, let's see, so we get t, t minus 1, t plus 2, negative t, e to the negative t, and x3 t is half t squared, half t squared, negative half t squared, minus t plus 0. This one is 2t. My pluses and t's look like the same. So plus 2t minus 1. And this one is 0, 0. Okay. So this times e to the negative t. So I've just rewrite and more simplified of those. And of course, the final thing, you know, is the general solution is the general solution is C1 x1t up there, C2 that x2t plus C3 x3. These problems are long. That was it. That was the end of chapter 7, guys. And I'm not gonna, you know, talk about 7.4 and 3. That's in just application.
Will we ever have to find those C1, C2, C3s?
If, let me add something, and if, yeah, initial conditions given, yeah. Conditions, you know, x1 of 0 equals a, x2 of 0 equals b. Yes, in that case, you're gonna have to find C1 and C2. Then we'll find the proper values of C1, C2, C3. Anything else? Ready for questions. If you have any questions, you can go ahead and open your mic and ask. If not, I guess we're done with the session. So if you have questions about the exam, I've already posted. Yeah, I posted the solution to quiz 7. Quiz 8 is in my office. So although I don't want to get out of my house, but I'll do it probably sometime later today. Okay, can you go over the procedure of the exam on Wednesday? Sure. So you just imagine you're sitting in class, except physically you're sitting at your house, dorm, I don't know, wherever you're sitting. You open e-learning at 4 p.m. The PDF version of the exam is going to be released at 400 on Wednesday. Okay. You open it, you're welcome to print it. If not, you can, just start writing the answers. So you grab different piece of papers, no line paper. Okay, it's hard to grade for me because you're gonna scan it and those lines are gonna mix up with your writing, and it may not make it as clear as it would be without those lines. So no line paper. Write your exams. You can use as many as pages possible. I would prefer you actually. Probably I'm gonna send out an email and have you do it this way. Write the answer to each question on a separate page. So use one page, even if it's just 3 lines. Write the answer to that question, to one question in one page. And then if there are 7 questions, that means you're going to have 7 pages, okay? And you scan it. I don't know if you want to take a picture and then load it to your scan app, or you want to just scan it at the same time. Make a PDF out of it. Make sure you name that file your first name, because I'm going to download all those files, put it in one single folder, okay? And then start looking at them and grading them. And then submit it to the Dropbox. So the length of the exam is going to be similar to the exam 1. It's going to be 100 minutes, except I'll give you 20 more minutes. I'll give you extra 20 minutes for you to be able to scan it and submit it to Dropbox. So I think the easiest way to do it is you absolutely imagine sitting in class. Don't do anything extra. And probably you know what I mean. Searching for answers is going to waste your time. So if you know how to do a certain question, if you know how to do whatever question you know how to do it, do those ones and then try to solve the ones probably you have some difficulties or you struggle with. Okay? Do not waste your time, because that's 100 minutes. And I close down. There's an end time on submission. So if that's end, you're done. Says, do we need to be here to mean like doing an online chat room? No, you don't have to. I'm not gonna, watch you guys as you're taking it. Like setting the camera, your face on the chair wherever you're sitting. So I trust you. I'm gonna have to trust you. So it's at 4 p.m. Open it and start answering. Submit it to the e-learning Dropbox. So I'll make a Dropbox. Okay, let's see. Let me go over the questions first. So solutions, yeah, I'll submit I'll post the quiz 8 later tonight. Procedure of the exam. So someone's asking, will there be a 3-tank problem? I don't know, dude. That's what kind of question is that? Do we need to be on a? Did we talk about it in class? Yes, we did. So there's a possibility that might. Do we need to be here? No, you don't have to. Thank you. This tab will be no. It's gonna be on Dropbox. You'll figure it out. Probably it's gonna be on. I'll open a module under content. Now you'll see the exam. So work and answer on the same page. You don't have to write down the question, okay? Just make sure you number it. So this is the answer to question blah. This is the answer to question 3, and then start your process. You can leave all your work. If you want to leave your work, it's okay. Of course, clean work. Don't use pen, use pencil. So if you preferably clean, but you can write your work on a different piece of paper and just final answer. It doesn't have to be, you know, all the scratch work, but make sure you show your full work. Okay, just the final answer alone, without any work, you're not going to get credit. Will the quizzes be the same as for exams? Sure, it's going to be the same thing. So it was 30 minutes. That means it's going to be probably 40 minutes. So you get 30 minutes to answer and then 10 minutes to scan and upload. Work and answer on the same page. I answered that one. It would find individual answers on both sides of. As long as it's readable and you draw a line. If you want to answer all questions in one single page, but if it's readable enough, if it's organized, if it's boxed, if it's nicely organized, then it's fine. I'm just worried about, you're just gonna start writing all over the place, and it's gonna be difficult for me to follow your work. If you can answer first question, draw a line, second question, draw a line, that's fine. Anything else? Let me give you a camera so you can see. Sitting in my apartment. Anything else, guys? Thank you, Les. Excellent. Very smooth. You're welcome. I'm gonna actually buy a different tablet. Found one. I figured there's another one that the typing is way better and more smooth. So, don't catch the virus. Sure, I won't. Thank you. You the same. Well, we're done with the lecture, so you guys are dismissed. Study. I'll be here tomorrow, noon to 1. So if you wanna, I was here actually. My chat room was open. So started studying. I already sent you what sections the exam is gonna cover. Study those. Go over the quizzes. Go over the exercise problems that I assign as homework. Go over your notes. Let me end this session.